You know that feeling, right? You write some code, it feels lightning fast on your machine, but then you push it out into the real world and it just grinds to a halt. It's not just frustrating for us, it means slow load times, unhappy users, and maybe even a surprise bill from your cloud provider. But what if the reason your code is slow isn't the computer at all, but a hidden pattern you didn't even see? Let's dig in and figure out what's really going on. So yeah, this is the big question, isn't it? We've all been there. You run a small test with, say, 10 items, and it's instant, perfect. But then the production version, with 10,000 items, just hangs. Why does the time it takes just explode like that? It doesn't feel proportional at all. See, the problem isn't that your computer suddenly got lazy. It's that the amount of work your code has to do is growing in a way you didn't expect. It's following this hidden, steep curve, and you just slammed right into the vertical part of it. So, to actually see these hidden curves, we need a special kind of language. And in the world of computer science, that language is called Big O notation. It's the tool that lets us understand, and more importantly, fix these performance traps. Okay, the number one thing you gotta get about Big O is that it's all about scalability. It's not about measuring the exact speed in milliseconds. Nope. Instead, it tells you what's going to happen when your input doubles or triples or grows by 1,000 times. It's how we describe the shape of that growth curve. So let's look at the two big ones you'll run into all the time. Over on the left, we have linear growth, or O of n. You can think of this as a nice, steady, predictable climb. Double the input, you basically double the work. Makes sense. But on the right, that's quadratic growth, O of n squared. And this one is sneaky. It starts off looking flat and harmless, but then it just shoots upward like a ski jump. And this chart right here is a perfect picture of that trap in action. Let's say an input of size n takes about 10 units of work. With that quadratic growth, if we just double the input to 2n, the work doesn't double to 20, oh no, it quadruples to 40. That's the ski jump. And that's exactly why your code feels like it's suddenly hit a brick wall. Okay, so theory's great, but where do these quadratic traps actually hide in real-life code? Well, they're often lurking in some very simple, innocent-looking places. Let's pull back the curtain on two of the most common offenders. All right, trap number one, and I guarantee pretty much all of us have written code that looks like this at some point. It's when you're checking if an item already exists in a list before you add it, especially when you're doing that inside a loop. Super common way to get unique items from a collection. But how you do it, well, that matters a whole lot. Okay, so look at the code on the left. That's the slow way. For every single item we process, we scan the entire result list from the beginning to see if it's there. As that list gets longer, that scan takes longer. Now, contrast that with the fast way on the right, which uses something called a set. So, what's the magic behind a set? Here's the deal. Using a list is like having a big, messy pile of stuff. Every time you need to check if something's in there, you have to start at the top and dig through the entire pile. The bigger the pile gets, the longer your search takes. The work just keeps stacking up. A set, though? A set is totally different. It's like having a room full of perfectly labeled boxes. You know exactly which box to look in, so the check is practically instant, no matter how many boxes are in the room. That's the power of hashing. It turns a long, painful search into a direct lookup. All right, on to our second common trap. This one is all about building up a string, piece by piece, inside a loop. It looks so simple just using plus equals, but it's hiding a massive performance problem. On the left, that's the code we've all written a million times. Start with an empty string, and then just keep adding new parts with plus equals. Simple. But on the right, the fast way does something different. It collects all the string parts into a list first, and then uses the dot join method just once, right at the very end. It looks like a small change, but the performance difference is just huge. And here's why. See, in most languages, strings are immutable. That means when you use plus equals, the computer can't just tack on the new part. It has to create a brand new, bigger string, copy all the old content over, and then add the new content. Imagine writing a long sentence, but for every single word you add, you have to recopy the entire sentence from the beginning. It's an insane amount of wasted work. Using join is like gathering all your words first and then writing out the final sentence in one single efficient step. So, we've seen the traps. Now let's flip this around. How do we systematically avoid them? Let's boil these fixes down into a few clear rules that can help us write code that's not just fast, but truly scalable. It honestly comes down to these three principles. First, if you're doing a lot of lookups, that is this thing in that collection check, always reach for a set or a dictionary. Their hashing magic makes those checks nearly instant. Second, if you're building a string from a bunch of pieces, collect them in a list and use join. Just do it. And third, this one's a biggie. Always look for expensive work you're doing inside a loop that could be done just once before the loop even starts.
At the end of the day, this isn't really about just memorizing a few code tricks. It's much bigger than that. It's about developing a new way of seeing your code, an algorithmic mindset that helps you predict how your code is going to behave under pressure.
In this quote, this really says it all. You can spend weeks tinkering with tiny details, shaving off a few microseconds here and there, but none of that is going to matter if you're still stuck on that quadratic ski jump. The real massive performance wins come from finding and fixing that one fundamental algorithmic flaw, from changing the actual shape of that growth curve. So, as we wrap this up, I'll leave you with this one question. Take back to your own work. The next time you're looking at a piece of code, just ask yourself, is there a loop here? And inside that loop, am I doing something that gets harder and harder as my data grows? Finding that hidden pattern, that's the first step to making your code truly great.